Okay, I don't know that we're going to have a whole lot of people here today. Um, so we got four people. That's not very many.
You may get more.
Uh,
It's
I
just
don't know.
three, so
Sounds
maybe.
like you have an interesting topic, though, Harry.
well, I'm glad you're interested in it, Robert.
Yeah,
Okay, so my topic was that cosmology and religion. And I think what happens when you're discussing that is you sort of have to be careful about definitions.
definitely.
Okay, this is the Cosmology Group meeting, and it's Sunday, and it's the 18th of May. Welcome, everybody. And I didn't really, we're sort of running out of things to talk about, I think. And so, what I thought I'd do is kind of make a review. And in a way, one of the ways you could review the idea of cosmology or the topic is to sort of put it in context. And that's kind of what I was thinking about. And the more I thought about it, the more I thought about the contrast between, science and religion. And so to start off, there's this book here, The Theories of the Universe. And the subtitle is this is a pretty old book, Milton Munitz, Munitz theories. This is I've had this book for quite a few years, and the sub title is From Babylonian Myth to Modern Science. Okay, so it's the myth part that's kind of he wants. We're talking about the myth. So cosmology, supposedly, according to this guy, starts off as myth. Okay, and so in religion, most people sort of refer to religion as um, uh, involving superstition. Okay, which I think so. Scientists say that we don't deal in superstition. Well, maybe we ought to take a look at that. Um, so from myth to modern science, I didn't really do a deep dive into this book. I just kind of took a look at it. It kind of dismisses the Babylonian idea, and it's poetry. That's kind of, you know, important, I think, to understand is that a lot of this stuff is poetry and says fundamentals of origin when a sky above had not been mentioned, when only primeval apatia their begetter. So there's a kind of an idea that there's an origin. And so then it talks about gods appearing, gods. So you have God. So the agency is some kind of a god, which I think brings in the idea of superstition. Um, but I think most of us are probably familiar with the um, New Old Testament, Christian religion, and I don't think it really says a whole lot about cosmology. I think it just kind of gives a broad brush, um, and there's really not a lot to work with there as far as a theory of the universe. He's talking here about a theory of the universe. So I guess we could sort of say, is that really what cosmology is? Um, I don't really know. So I'm going to kind of open up for discussion. Does anybody have any opinions about um,
Yeah,
what is the purpose of cosmology? Is it to explain the ultimate reality, or is it just um,
well, I would say that, and the origins of reality and the world. We know there was a Genesis account, of course, which covers sort of how things began. That let there be light, and create like the 6 days of creation and such. That sort of that's at the very beginning of the Old Testament, of course. I mean, religion was sort of. I mean, it was a type of philosophy early before there were critical standards. Really, that there wasn't anyone really around to say. I mean, they felt the need to answer these questions. They were trying to make sense of things. They're asking the how, like, how are we here? And so. Of course, children are inquisitive. They ask, "Well, how did we get here? Why are we here?" They had to come up with some sort of answer to satisfy everyone, just to maintain order. It seems, because where would they be without something to believe in? I mean, of course, maybe that was suitable for their day. You know, um,
So you brought up the critical issue, which is the answer to the how question. When that I think is the key point. So what we have is we have stories that answer the how question. Okay. Now I notice that Jim's not here, and part of the reason for my initiating this conversation was because he's um, uh, brought up the issue of, well, I forget exactly what the term they used was, an origin story. Does that sound? Is he here?
No, I think he was talking about creationist theories, Harry.
Yeah, but an origin story, and he referred to it. Well, I'm talking about last week when you weren't here, and he referred to it as a derogatory term, origin stories. Like the word story is kind of derogatory in my opinion because it implies that it's just like a myth or that sort of thing, not necessarily true. It's just a story, and I think Jerry was talking about that. So maybe cosmology begins in stories that we tell children when they ask the question, why are we here? How did we get here? That sort of thing. So my point is modern science actually helping to answer that question or not? So is modern science what they claim to be true? Is that just another kind of story that they've made up?
well, I actually haven't been ever really totally clear of what all cosmology covers, as far as, I mean, the Big Bang is a cosmological theory, of course, which has been the dominant theory for quite a few decades. However, though, there are many flaws, of course, that we recognize. And I mean, what else does cosmology deal with apart from the origins specifically, just the nature of reality and such? Just
Well, that's a kind of what I'm trying to get at here. Um, so in this book, I'm going to shift gears a little bit. I've been reading a different approach to cosmology. This is the Fred Hoyle, um, Jeffrey Burbidge, and Jayant Narlikar, who's an Indian fellow book. I've talked about this. And a different approach to cosmology from a static universe through the Big Bang towards reality. Okay, so and the subtitle here is he's sort of because this is written by, I think Hoyle is influential. Do you know who Fred Hoyle is? Or are people here familiar with Fred Hoyle?
I've heard
Yeah,
of him.
Yeah, didn't he defend like a steady state cosmology?
Well, he would sort of claim to be the inventor of it, but or co-author of steady state cosmology. But he's a very famous astronomer.
perhaps even the inventor of the term Big Bang.
Correct. In the derogatory,
Yes.
his intention was to the term Big Bang is derogatory. It's not a positive affirmation. He meant it to be derogatory. So Fred Hoyle, you know, he's written many books and popular astronomy. So he's well known if you read many of his books. Back in when I was growing up, he was like one of the books that you sort of had that was a must read if you were interested in cosmology. and popularizer of astronomy. But you hit the fine points. He came up with this um, steady state theory. Okay, and I think about 1948, and I'm not. I haven't really researched it. He doesn't really go into detail in this book. He does mention it, that Bondi and Gold apparently have a sort of a variation or a different type of steady state cosmology. Um, he doesn't really go into details in the book to explain what the differences might be, but the idea of a steady state cosmology is that creation is a process that goes on. Okay, that we can observe in the present rather than something that happened in the past. Okay, does that anybody have any questions about that definition of what
Well,
steady?
I would say, of course, we can only observe the present. I mean, throughout all of history, that's only what's been possible. However, we have to make conclusions, or at least speculate as to how things began, or if they did begin. Uh, you know,
Well, you observe into the past, though, since it takes light time to travel.
well, yeah.
Right. Well, the point is, okay, so I want to get a little bit here to um, kind of the main idea is that let's go back to what he starts off with the story here in his book. He starts off with Einstein, which I find kind of interesting um, because this guy, Munitz, in his book, or Theories of the Universe, he goes back to Babylon. Okay. And then there's a lot, I mean, very, you know, only this last thin part of the book is Einstein after Einstein. So there's a lot of stuff between, there's a pretty thick book, and maybe 85, 85% of it is before Einstein, right? Why are we starting with Einstein? That's kind of would be my first question. Why does a book on cosmology? I think if you find most scientific books, they basically ignore anything that happened before Einstein. So why are we starting with Einstein? That would be my first question.
Why aren't we starting with Einstein?
Well, why does science start with Einstein? Okay.
Well, it doesn't. I mean, I wouldn't say it does. I mean, Newton and Galileo were highly
Now
relevant
you
compared to a lot of
misunderstood
them.
the science of cosmology.
Yeah.
So the science of cosmology, if you would, they would you get an introduction chapter on a book on an introductory book, and it would give you like, oh yeah, maybe a chapter on all this. 85% of this book would give you like the first chapter in a book on cosmology, and then they launch into Einstein and why our current theories are so much better.
Well,
Uh,
Einstein wasn't per se a cosmologist, but they would claim, the mainstream would claim that his theories have upended all our ideas with regard to physical science, and therefore all our ideas on how the universe works and indeed its origin.
right. So we got a blank. So we're just going to wipe off the slate and start with Einstein. I've seen that actually. I saw a video today where the guy was actually trying to say what you just said, which is, you know, everything before Newton's theory and all that stuff before Einstein, doesn't matter. It's wrong. We're only right once we start with Einstein. Okay. Um, I think the real issue has to do with um, if you were a scientist, the whole business of astronomy evolves from the study of the motion of the planets. Okay. And so to do that, you have to have a law of gravity, which Newton came up with, a law of gravity. And so everything about cosmology is based on gravity. That's it. That's Einstein has a law, a theory of gravity, and so that new theory is correct. So we have to go with Einstein's theory, right?
Well, I remember reading a book called that Einstein wrote, the Cosmological Considerations of General Relativity. It was written a year after he published General Relativity, and it's filled with outlandish ideas. It was way before the Big Bang. So he had the idea that the universe could be infinite in time, but finite in space, or finite in space or infinite in time, or finite in both. However, though, he didn't consider that each could be infinite, which I
Okay.
thought was interesting.
Um, okay, that was good. That's a good introduction to what I'm gonna talk about, and good segue into this. Okay, so in this book, he talks about they talk about the history of it, and they give a pretty good overview of the history. So Einstein had these equations, and so he published these equations, and then you have De Sitter, Friedman, who are trying to solve these equations. So Einstein had a solution, and his solution was unstable, and so he added the cosmological constant. You also had De Sitter. De Sitter solved the equations, but his universe didn't have any matter in it. It was an empty universe. So imagine this: they were able to solve Einstein's equations when there was no matter in the universe. That's a bit bizarre. Um, and then Friedman, who was working in Russia, I believe he was Russian, uh, solved these equations. Okay, so while this is going on, you also have the astronomers are arguing about galaxies and whether galaxies are outside of the Milky Way or part of the Milky Way. And this is comes to a head in the 1920s, which is right after Einstein comes up with his theory. So I think there's a issue here about a theory being advanced and in the theoretical front and foundational work that's going on in a completely separate compartment of science. And they're measuring these redshifts of galaxies. So what happens is they eventually decide the galaxies are outside of our own galaxy. And prior to doing this, they'd also measured the redshifts of galaxies, not very many, a couple. And this guy Slipper is the main protagonist in doing this. And now this was done when spectroscopes were very crude and not very sensitive, and it was very difficult to make the measurements of spectrums of galaxies. And I think one of the issues was, are these objects composed of stars or are they gas? And of course, when early measurements were made, they found out that they had spectrum that looked like stars, but the spectral lines were shifted towards the red, which meant there was a recession velocity. So what happens is, to jump to the quick story, Hubble comes along and takes some of the measurements that had been made by Slipper. Now you have to, and the other guy was named Hugh Mason, and they were working at I believe they were using the Hooker telescope, which is Mount Palomar's 100-inch telescope, which at the time I think was the biggest telescope in existence. And so Hubble definitely established, he was able to establish that galaxies were outside of the Milky Way and they were real far away. And he then also established that they were moving away from the Milky Way, and he came up with this redshift redshift distance relation, and that was in the 1920s and towards the end of the 1920s and the 1930s. Now, this kind of happens at the same time that the theoreticians were coming up with these theories of solutions to Einstein's equations that showed that the universe was unstable, meaning it was expanding. Okay. So, because there was a coincidence between the redshift and the theory that said that the universe had to be, look like it was expanding, they started studying these models, which are called the Friedman models. And the Friedman models basically is a differential equation that has a bunch of parameters in it. Okay, so the universe could either be finite and bounded, infinite and unbounded, and flat, which means it would be infinite, unbounded, and flat. And the other one would be infinite, unbounded, and expanding, continuing to increase in its rate of expansion. So there's these different solutions. And Hubble was interested in in determining which of these solutions. So you think about this, they just discovered that galaxies existed outside of the Milky Way. They just discovered that galaxies, and Hubble was so ambitious, he thought he could find the equation for the universe by making these measurements. And so he had this program where he was going to try to make these measurements. And the idea was if you could measure the distance and the redshift of galaxies further and further away, you could determine where on this curve of the different universes the actual universe exists. And that's kind of where we stand in the 1940s. Now, he wasn't very successful with it. So I'm going to get to the point here.
Can I raise a point?
Go ahead.
You mentioned two variables, the distance and the redshift. Could you remind us how the distance is quantified or defined operationally? What measurement gives you the distance of a galaxy?
They measure the brightness, and then they have a bunch of calibrations. Now, this is where the
brightness. Okay.
So this is where the issues come into play. What is the brightness of your standard, what they call standard candle? Okay, what's the brightness of your standard candle?
Okay, thank you.
What's the calibration of the brightness of the standard candle?
Anyway. Actually, I remember reading in a book by Eric J. Lerner, The Big Bang Never Happened, of how he knew people who had observed the redshift of various galaxies for decades. And then he found that some of them that were highly redshifted would sort of lose quite a degree of the redshift over time, which
I don't
seems
know anything
possible.
about that, so I can't comment on that.
Okay.
So is the amount of redshift inversely correlated or directly correlated with the distance in terms of brightness?
Well, you sort of jumped the shark here. That's kind of questionable. This whole idea is kind of questionable. That's kind of the point that I was getting to before you interrupted me.
Oh, okay. I didn't want to mess up your presentation.
Well, so this is where we get into
educate myself a little bit here as to be able to follow your presentation. Thank you.
You're probably going to come to this as well, but Harry, they calibrated the brightness of these elements by indicating or assuming that the period of pulsation of these variables.
Okay, you're talking about Cepheid variables.
Cepheid,
I skipped
exactly.
over that because it's kind of belaboring a lot of the technical fine points. Hubble basically, what they did was they looked at stars in the Milky Way that they could figure out how far away they were by their variation in brightness. And then they looked at stars in Andromeda Galaxy and found similar stars and then assumed that they were the same, physically the same. Notice the assumption of they assume they're physically the same. There's no justification for that assumption. Okay. And then because of that assumption, they made a measurement and were able to calculate supposedly calculate the distance, but it turned out the distances are way off, okay, from what we know today. But um, that's kind of not really the point that I'm really trying to get at. The point I'm trying to get at is that this whole idea of the redshift distance relation, okay, is where we get into, are we talking about cosmology or are we talking about religion? Because this idea that the distance redshift relation is true is questioned later, okay? And there's this resistance to the idea that you can't question the distance redshift relation. And it almost sounds like the anger that Galileo provoked when he said, the church is wrong. The sun isn't the center of the universe. And supposedly the church reacted with extreme dogma and censored him and all these other things. Well, basically, the science community did the same thing to people who questioned the distance redshift relation. So, are we dealing with science or religion? Okay. Is this science that they're talking about, or is it religion? They don't want to accept the data. So that's a large part of
Well,
what it's about.
you can be dogmatic without basing your dogma on religion. So just the fact that it's dogmatic doesn't make it religious.
I realize that. My point being that normally we do associate dogmatism with the Catholic Church because of this incident that I described with Galileo. Is that not correct?
No, that's right.
And
Well, religion and all other avenues of human uh, endeavor are really majoritarian views which are formulated for various reasons. And then they become by nature dogmatic. And it is disappointing to a person perhaps like me who early on thought that science was quite different from religion and that religion was based on faith and just dogma, but science was totally open and based on evidence. Well, in actual fact, when you start looking at it, you find that science has many of the attributes of conventional religion. And not only physical science, because it would be very strange if it were just cosmology. Politics and psychology and medicine and jurisprudence, all these things have accepted theories um, for which people who question those theories get very short shrift.
right. So, but science is supposed to be um, uh, the search for truth, right? I hear
Supposed to be.
academics use that term a lot, and is that what it is? The
Disinterested
search for
pursuit of
truth?
truth.
Well,
So that they're, yeah.
I would say ideally it is a search for truth, and that many would want to uphold that. However, though, it's a sort of a natural human reaction to, act adversely when, one's cherished beliefs are challenged, especially when they have the weight of majority rule type of
Right.
incident.
All right. I'm going to give you my point here that I'm going to talk about, and because we got about 10 minutes to go. My point is, I'm going to present two examples in cosmology where it kind of science didn't really behave in the way that it's the search for truth. And the one example is the steady state theory that Hoyle proposed. And the other one is the redshift distance controversy, which primarily involves the redshifts of quasars. Okay. And in both cases, it's well documented. There is the establishment lined up against these ideas. These facts can't be accepted, type of thing.
Well, I would say as far as the steady state theory goes, uh, I don't agree with the spontaneous creation. However, though, it proposed a static universe that doesn't expand, however, that it's infinite. I agree with the infinity part. However, though, I don't know if the universe is static or if a portion of it expands. I think it's possible that there are objects rushing away, galaxies and such, though I don't think it's the whole universe that expands, because if it's infinite, what would it expand into? I think it was possibly caused by a local explosion, which sent things rushing away. Just a thought.
Well, you've brought in a whole lot of different controversial topics there that you kind of threw into the mix, and maybe we need to sort of separate them out a little bit. Um, uh, I'm not sure that the steady state theory accepts that the universe is expanding, and it invokes what, according to Bondi and Gold, they have what's called the perfect cosmological principle, which I don't know that Hoyle necessarily embraces. And the idea is that if the universe is expanding and it has to be homogeneous, okay, so you have these philosophical ideas of homogeneity. You have the perfect cosmological principle. The universe is the same all places and all times. So if you go back 10 billion years and you look at the universe, it looks the same 10 billion years ago as it looks today. That's the perfect cosmological principle. And the idea is if the universe is expanding, that means that the galaxies would get less and less numerous, okay, because they're expanding apart, right? And so if the galaxies are getting less and less dense, the density of the universe is decreasing. Therefore, according to the perfect cosmological principle, something has to be created. Galaxies have to be created in order to keep the universe the same, okay, at all time. You understand that? That's
Well,
where the
I
that's
mean,
where the creation comes from. So matter has to be created in order to fill the emptiness, that would result from the universe constantly expanding. So the density would decrease. So you need to create matter in order to make up the difference.
So a negative way of expressing that might be that if you accept a steady state theory and you want to keep to that, and then you also accept an expanding universe theory, well, then you have to introduce this parameter uh, in to save the steady state theory, namely continuous creation.
Well, okay, you could look at it that way. Um, the I think the whole point of it is that it adopts an assumption, and then a consequence of that assumption is the continuous creation of matter.
so the continuous creation would fill in the gaps as galaxies rush apart
Well, the
or
perfect
something.
cosmological principle. Now, remember, this is just a principle. It's just something that they invented. It's just like Einstein invented general relativity, and he wrote all these equations based on what was his postulate. You should know what his postulate is. What's his postulate? The speed of light is a constant everywhere. Mm-hmm. That's his postulate. He creates a theory of the universe and gravity based on that one postulate. The speed of light is a constant
in a vacuum.
Yes. Well, anyway, that's the whole thing. I mean, so that's his principle, and then they extend that to get to solve these equations. You can't solve a general relativity equations. There's like umpteen parameters in the equations of general relativity. So what they do to get around that is they add in a bunch of simplifying ad hoc assumptions to make it simple. And by making it simple, that allows them to solve the equations to simple equations. And I explained the results, Friedman and these guys. So they spent all this time trying to come up with these ways of simplifying Einstein's equations so they could get simple equations from complicated equations based on the assumption that the speed of light is a constant. Okay. And then adding in all these other ad hoc stuff in there to make things work out.
But it seems like you're mixing uh, special relativity with the assumption of the constant speed of light with general relativity in your comments there, as
No, I'm not.
as if they're just one.
That's the fundamental. The general relativity is based on special relativity, and the assumption that's foundation of both of them is the speed of light is a constant. The difference is that the speed of light is a constant in curved space-time manifolds, whereas in special relativity, the speed of light is a constant in flat space-time.
Well,
There are other things added, such as the equivalence principle, but still,
What you have to add into, that's another one of those points I'm making. You have to add in these ad hoc things, these additional postulates to simplify the thing to get it so you can write down equations. And so after Einstein's done this, he's got this complicated set of tensor equations, and they start trying to solve these tensor equations, find out they can't really solve them unless they add in simplifying assumptions. Okay, but
Question. I'm recalling that some people have concluded that in terms of space-time curvature, that the universe is in fact flat, so that this would seem to exclude or set aside general relativity. I mean, if astronomers and astrophysicists have concluded that the universe is flat, then we don't have curvature and we don't need general relativity on a universe-wide scale.
Well,
does that make any sense?
The current standard cosmology assumes the universe is flat, if I'm not mistaken.
Yeah, that's what I'm saying.
They added in, I talked about this previously, they added in dark matter to make it flat. And it's not real clear to me why they did that. But that has to do with what I was talking about. And I didn't really get to my story, which is that Hubble was trying to determine by doing his, it's explained in this book, which, you might want to read, that Hubble was thinking that I could measure these galaxies, a part of the justification for them building the 200-inch Palomar telescope, they said, oh, we can discover the law of the universe by measuring galaxies at further and further distances. And so we build this telescope, we're going to make this big accomplishment. Great, we'll solve the puzzle of the universe. Okay, give us the funding and we'll solve this. Okay, we're going to get off of here pretty quick, I think. Got about a minute to go. So that was the justification for building the 200-inch telescope. It was this program of we measure these galaxies, we go further and further out, we measure the redshift, we get the distance from the redshift. The distance is proportional to the redshift based on the Hubble law. We measure the redshifts, we go further and further out, and then that'll tell us which equation the universe conforms to.
So do we have simple scatter plots of the redshift with
you go and you go online and you look at cosmology and textbooks books like this and textbooks in cosmology, they give you the scatter plots. And they do these least fit regression studies and all this stuff. The bottom line is that Hubble's program doesn't work. They don't have a solution.
To Jim's point, the universe being flat does not imply that there's no curvature to the gravitational curvature to the universe.
All right, now let's see. Where do we stand? You were interrupted there.
Yeah, I was just saying that the universe. You hear me? Okay.
Yes.
Okay, I was just saying that the universe being flat that Jim was speaking of does not imply that there wasn't a curvature, gravitational curvature around objects and planets and that. What it implies is that throughout the universe, matter is evenly distributed.
Yeah, that's questionable.
Well, I mean, that's what the universe being flat implies. That's what they're saying when they say it's flat. They're not saying that there is no curvature due to gravity.
Right. Well, okay. Anyway, all right. So we're sort of like a part of the way through the story that I'm trying to get to, which is we talked about the Hubble and his um, basically they sort of abandoned. They tried to do this idea of by measuring further and further away, and then they started using quasars, but quasars didn't work out, and that's part of the story that I want to get to. Um, so there are two parts of the story. There's the steady state theory, and there's the redshift issue. Okay, and so we talked about the steady, both of them. Okay, now at the time that the steady state theory was introduced, they discovered radio galaxies. I talked about the history of radio galaxies. And this guy, Martin Ryle, okay, he had this idea that by measuring radio sources, as you go weaker and weaker, you would go further and further out into the deep part of the universe. They came up with what we call radio source counts. And Ryle apparently was one of these people who had this arrogant notion that he knew what was right, and he didn't like the steady state theory because, like, for whatever reason, he was an arrogant guy. And he put out a paper in about mid-50s in which he proved that the steady state theory was completely false because of his measurements of radio counts. And Hoyle in this book documents this. So this is an example of a theory that got killed by false evidence. So we got to have a problem here with false evidence. Now, how many people out there know that this evidence that supposedly disproved the steady state theory was wrong is false? Anybody heard of this?
What do you mean by false? It's been debunked, or there's a
they proved
a
it was
methodological false. Error?
They proved that the measurements were faulty and that the claim that he made was false.
I believe it is false for other reasons, for theoretical reasons, but I wasn't quite aware of some of these maybe fabrications of the evidence that I think you're referring to, Harry.
Well, I don't know that there were so many. It just didn't. It's a kind of a technical argument. It's basically discussed in this book, and I've only actually seen it thoroughly discussed in this book here. Different approach to cosmology. Hoyle apparently was really upset about this. He goes into the political aspects of it too, where he talks about how they tried to hide the data from Hoyle. So apparently Hoyle worked at Cambridge, and he apparently when he'd come to visit, they'd hide all their data to make sure that Hoyle and any of his associates wouldn't be able to see the data, So they were very secretive. Now, this is kind of how science works, right? Science, is this supposed to be how science works? Apparently, it doesn't work that way. Okay. The point is, and I don't really, I could probably spend a couple of hours talking about this controversy about the radio sources' disproof of the steady state theory. But what happened was that everybody believed it because this guy, Martin Ryle, who was the head of this fancy laboratory of cataloging radio sources, he decided he was going to kill Hoyle's idea, and he did. Okay. And it only is later we find out that his data was not really valid and his claim wasn't really valid, but he killed the steady state theory pretty effectively. And we don't hear, and essentially it's pretty much dismissed in the textbooks. So that it's dead. He killed it. It's only been like less than 10 years and he killed it dead. Okay, so the question, go ahead.
So then sorry,
Well,
but we're back to the original question. Why did he do it? Was it for professional reasons, or was it a religious thing that maybe he was influenced by early teaching that the universe must have a beginning, like a creation, and he wanted to get rid of any sort of theory which contradicted that?
Yeah, that's a good question. We don't have an answer to that. But so my point is, yeah, maybe religion did have something to do with it. I don't know. You know, but it does. It's a kind of a dogmatic sort of thing. Why would he kill a theory? Um, maybe he didn't like. Maybe he's like Jerry. He just found the idea of continuous creation absurd and ridiculous.
was that his primary objection, or did he also disprove, like did he show that the redshift indeed suggests distance and relative high velocity?
All right. There's no redshift measurement of radio galaxies. What he did was he counted the number of galaxies as you went further and further out. Okay, so as you go further and further away, you should count more and more galaxies. In other words, as the flux, the radio flux, the brightness measure, if you will, of a radio galaxy, as you go further and further away, that flux should decrease according to a certain law of distance. In other words, they calculate how the brightness should decrease as you go further and further away. And you can come up with a mathematical relation. And he showed that they didn't obey the relationship that was, he claimed, predicted by the steady state theory. Now, this is an instance of where he interpreted the steady state theory to mean what he thought it meant. And so when they plotted the measurements versus the prediction of the curve, they didn't agree. And so he said that made the steady state theory incorrect. Does that help you? This is a pretty complicated technical issue.
Well, so it was primarily the redshift that
No, there's no
made it up.
redshift involved in galaxy counts.
Well, okay. As far as seeing the redshift, like to determine the distance of galaxies, I mean, it should be obvious that when we zoom in further with telescopes, that we might see a little star. It looks like a star, and we zoom in further, we realize, hey, that's a whole galaxy. We realize that's further away. So I'm sort of unclear of how the redshift determines distance or
No, there's no.
velocity.
You're confusing radio with optical. Okay, now Hubble
The
also,
redshift,
huh?
the redshift doesn't determine distance of galaxies. It determines the motion of galaxies. What Jerry was saying, it determines the distance of galaxies, and that's not correct.
I was saying distance and velocity. Distance is
Velocity,
obvious; it's further away, but it also travels at a very
yeah,
fast.
but it
Only if you
it
accept that these are Doppler effects.
right. The brightness determines the distance. The
Really,
redshift
I
determines the
didn't know.
velocity.
Oh, okay, I didn't know.
Well, this is kind of a technical issue, and I'm trying to squeeze a lot of information into a short period of time. The main point I'm trying to get at is that uh, apparently the steady state theory didn't agree with the religion of the scientists at the time, and so they suppressed his theory. And and as documented in the book, A Different Approach to Cosmology, if you were to believe or accept Hoyle's version of events, it wasn't exactly done in a fair and square way. The fact that they hid the data didn't really give him a chance or an opportunity to, when the results were published, they sort of played dirty with the way the announcement was made. He was invited to the press conference in which they announced the results that the steady state theory had been disproven. And after he made this announcement, this is in Britain, the press went over to Hoyle and asked him, what is your comment? What do you have to say to this result? And Hoyle couldn't say anything because he didn't know anything about they never sent him a preprint of the paper. And so he was left like, couldn't say anything, right? He was left. And so that just worked more to the advantage of the Martin Ryle and the people who were trying to kill his theory, because he couldn't respond because they kept everything secret.
So when did you say this was? The 1950s?
Yes,
Long before the CMB, for example.
This CMB wasn't discovered until after in the 1960s.
And this happened in the 50s, what you're
Correct.
talking about. Okay.
Well, and the initial thing happened in the 50s, and there were Ryle did further claims. He released later information. What he was doing is he was compiling a catalog of radio sources. So you have a catalog of radio sources. You measure their brightness or their intensity in the radio spectrum and plot their position. And you put it in a catalog and give it a name.
The popular literature, which doesn't go into it in such detail, says there were many questions about the steady state theory, but the final nail was in the coffin was the CMBR in 1960.
Right. Yes, that's another example of so if we say that religion is based on myth, okay, and stories, then that's one of the myths in the stories you just described. You could say that's a myth or a story that they put forward in the textbooks because they want to make it look like, you know, they've got the answer in the Big Bang Theory. Big Bang Theory is right because we discovered the microwave background radiation. Now, Hoyle in this book, they go into that in here, and he points out that the predictions of the Big Bang Theory didn't work out with the measurement of the microwave background radiation. The prediction was 10 degrees K, and the measurement was 2.7 K. So what rules of science are you using when your prediction doesn't work out?
Well, I would say that if you're highly invested in a theory, you might want to interpret anything that resembles evidence as, well, hey, I can use that in favor of my theory. I mean,
That sounds kind of like what religion does, right?
well, sort of. I mean, yeah, essentially, I would say.
No.
So it's like you're fudging the evidence. So in the book here, in a different approach to cosmology, they make this point. They say if we're supposed to believe in predictions, that science is based on predictions being correct. When you make an incorrect prediction, okay, that means your theory is dead. But that's not exactly how science works. Because in modern science and cosmology, you've got all these ad hocs. Okay, remember I was talking about all of the simplifying assumptions that you use. So, so what they do is they go back and they say, well, how can we change our theory to agree with the measurements?
What's that?
How do we change our theory to agree with our measurements? So that's what they did.
Huh. I was wondering if they're going to have another auction or something like that. Maybe,
all right.
A couple of legs.
Cornelius.
Maybe it's to be donated.
All right. So everybody understand what they did there?
Well, it's parallel with the analysis of the 1919 solar eclipse Eddington data. That was fudged up as well. But that's accepted generally now by the scientific community. And yet, if you look at the original paper, it appears that the data were just twisted around to suit what they wanted to prove.
Yeah. So
Well,
we're dealing with a search for truth, or are we dealing with dogmatism
well,
and
actually, I would very much agree with Ian that that what Eddington wrote. If you read what he wrote, it wasn't at all scientific, and they had the preconceived bias. They wanted to prove that light deflected. However, though, I've heard other physicists say that they have more advanced technology now, and they can observe the deflection of starlight even when there isn't an eclipse. So I'm sort of on the fence. I don't really know what to think, but I think Eddington's original journal of his investigations weren't valid.
well, that's an example of an incorrect prediction, then, right?
Yeah. However, though, I've heard other people say that since then there's higher technology developed that can determine that there is indeed deflection of starlight, which
So now we have ad hoc assumptions added in. So if the theory doesn't conform to the observations, we can change the observations or the theory.
And the
And
important thing is once you've done that and it becomes accepted theory, well, then it's very hard to uproot. And all conventional scientists have to say what they said to Jerry or what you've read. Oh, this is an established theory, and we now have uh, equipment which is millions of times more accurate than what they had then. And you needn't worry, we've proven that it is so. They don't have to show you that from first principles because the theory has already been established for maybe 100 years.
so I guess now we can understand why the Catholic Church said Galileo was wrong, because he's
Well, there
disagreeing
are
with.
two schools of thought. The majority in the Catholic Church would say he was right, but there is a small number of people who would say he was wrong. So,
Well, maybe
but
currently, but at the time, I'm talking about at the time. So they
well, yeah.
basically censored and suppressed Galileo. The argument as to whether Galileo was right or wrong is kind of like not really part of what I'm pointing out. I'm pointing out that the establishment suppressed his opinion.
And I've heard sort of religious scientists say something like, well, he possibly was right scientifically, but it was right to persecute him because he was questioning the veracity of the Bible, and that's unforgivable.
Yeah, okay. So we have you're questioning the veracity of the scientific establishment and all of our assumptions. Can't have that.
That's right.
Um, so we have sent that, so you have the mechanisms of censorship. Um, what is it? Censor, dogmatism, intolerance, dogmatism, censorship, suppression of dissent, those things. And we see them operating in cosmology. And so
Well,
it's
we don't normally discuss politics, and probably that's a jolly good thing. But I mean, in the modern world now, it's permeated everything. So if you don't concur with a political view or a social view or a psych, you're cancelled. So that's the same thing, exactly the same thing. You're not allowed have a contrary view to the established orthodoxy.
right. Uh, well, you still have what you have now is in the case of the universities don't like it if you don't teach what they want taught, which are things which you've said, which are politically popular things. So there's a lot of dissent in the universities, but that dissent has been eliminated because they fire the professors who don't toe the line. So you could wonder, is this same thing operating in science? Well, actually, we have an example of that, which would be Halton Arp, okay, who wrote this book here, Quasars, Redshifts, and Controversies. They didn't like what he was finding. He was observing things and finding facts, and they didn't agree with what the prevailing dogma was. And so they took away his observing time for the 200-inch telescope, which essentially, if you're a staff astronomer at Mount Palomar, this is it's kind of associated with a university. So you got this academic committee deciding, how they were going to allocate the telescope time. They didn't like what he was finding when he was given telescope time, so they took away his telescope time. You take away your telescope time, you can't take pictures of things and find things that don't fit into the accepted theory.
And of course, the well-known phenomenon of one of our own members, perhaps he's not very active at the moment, was Bill Lucas, where the president of his university called him in. Now, he didn't want him to stop what he was doing, but he said the federal government, which is funding a score of our projects, has told me to fire you or they'll stop the funding. Now, presumably, the people who told the president to do that were sort of pen pushers. They probably weren't scientists, but they were following some orders, policy.
Yes, that's another example. I'm very familiar with that. So, if somebody is doing research in science that doesn't fit the accepted belief, you get rid of him. You defund him. you don't let him publish his results. That's the other technique that Halton Arp talks about. How you have these referees and they object to your paper and won't let try to do everything they can to prevent it from being published. That's another of the tactics.
And of course,
okay.
the German Galilean electrodynamics, which is a bit defunct at the moment, has as its policy or the reason when it was created to alleviate the position whereby people who criticize Einstein's special relativity couldn't get published in any journals at all. So they said, well, we're not like that. We're an avenue for such people to publish.
Yeah, okay. So let's see, where do we get to? I talked about the steady state theory and the radio source counts and the claim that the radio source counts disprove the steady state theory. And so that theory is dead. Okay. Pretty much that pretty much killed it. Although Hoyle is, I think this was the last book that he wrote. This book here, the one that I'm talking about, I think this was his last hurrah. I could be mistaken, where he sort of summarizes his experience with the scientific community. Okay, the next issue that comes along is quasars. Okay, and does anybody need a discussion of what a quasar is? And
I wouldn't mind a refresher.
Okay, quasars were discovered about, I forget, 1963, 64, where they were trying to identify radio sources. Now, remember this guy Ryle, and there were some other people who were doing it. There was an Australian group, and there were other groups, and they were compiling these radio catalogs. And the idea was, what is this object? What is creating this radio emission? These really strong radio emissions. And so to do that, they had to get optical identifications, they're called. So they would get a position in the sky of the radio source, and then they would look where that position was and see what was there. And as the accuracy of the radio positions got better, they came across this objects that weren't galaxies. And originally, they had identified the radio sources with what are called supernova remnants and external galaxies and H2 emissions, and H2 regions, that sort of thing. And so when they were trying to identify, I forget the particular number of the quasar, but anyway, they looked there and there was a star. Okay. And, that kind of surprised them because in the past they'd found either a supernova remnant or a gas cloud or a galaxy or But, just to find a star was kind of a surprise. And when they measured the spectrum didn't look like a star. So it couldn't be a star because it didn't have the spectrum of a star. And so that was a puzzle. And then eventually, one of the people who's famous for this, and I forget his name, but anyway, he looked at the spectrum and discovered that the spectral lines were shifted and it had a very high redshift, very unusual, relatively high relative to any galaxy that they'd measured, an extremely high redshift. And this caused a problem because the quasars were pretty bright, but if the redshift distance relation was correct, it had to be further away than any galaxies that they had ever measured. Okay, and so they had this problem of where does all the energy come from for this star, quasi-stellar object, they're called. So it looks like a star, but it's way 1,000 times more bright than any star or galaxy, brighter than galaxies. So this is a problem. And one of the proposed explanations was that the redshift is not a correct measure of the distance of a quasar from the Earth, and that would alleviate the problem of why it's too bright. In other words, it's too bright. If the energy that would be needed to explain its brightness is just way out of all proportion to known physics. Okay. Then there's the other problem, which is that in quasar 3C273, they discovered what are called superluminal velocities, which means that the objects that they're observing are moving faster than the speed of light by many times. So it's moving faster than the speed of light, which kind of is a problem. So anyway, does this kind of help you to understand?
Oh, absolutely. I often get them confused with nebulas. Or nebulas, is that what they thought? They thought it was something on its own, but when they zoomed in, they realized it was just
All
distant
right.
galaxies.
All right. So anyway, there's a little bit more to the story.
Okay.
It turned out that when they started looking, they determined that these quasars had blue. They were blue, which is kind of confusing. Why would they be blue if they're redshifted? But anyway, and so they came up with this technique of looking for quasars on blue sensitive photographic plates. And so what interestingly happened was that they discovered there's a whole group of quasars that don't emit radio, that are not detectable in radio wavelengths. Okay, so now you have two classes of quasars. You have quasars that emit radio waves and quasars that are radio quiet. And there's two different distinctions. And so when they measured the redshifts of the quasars that were radio quiet, they found they were redshifted as well. And, I can't really comment on why they're blue when they're redshifted. That's kind of confusing. Okay. And there's more of an explanation to that than I can go into here. Okay. So what does this all mean? So then they said, okay, well, we can use these quasars because they're so bright. We can use them to explore the structure of the universe. And so we'll plot the brightness redshift relation for quasars. Okay. And when they did that, they got a very bad result. There is no distance redshift relation for quasars. And so that's not good news. Yeah, you're laughing.
Well, no, I mean, at that point, I think usually the music track would come in with a dunk dong.
Yeah, right. Now,
Okay, continue, continue.
I can't, there's a plot of this in here, but the scatter diagram is what happens is that the plot of quasars, it goes like this and then it comes down real quick. So in other words, there's a certain redshift at which very few quasars exist past this redshift in their plot. And so this is a big problem because now the redshift distance relationship isn't working. So can we guess what happened when this evidence came out?
Another fudge, I presume.
Well, it
Great
was
detail.
more like well, we're right. Our Big Bang model is right. So we can't accept this idea that the redshift is not related to distance. And so Art, talking a bit about Art in his book, this is Quasars, Redshifts, and Controversies. He discovered quasars that were close to bright galaxies. And says, that's interesting. Why are quasars near these galaxies? Now, Harp was kind of a proponent of the idea that quasars weren't really as far away as the redshift indicated. And the reason for people believing in this was, well, they're too damn bright. I mean, where's all the energy coming from for these things? They're too bright. They can't be as far away as the redshift says they are. So he discovered these quasars. Here's a picture of one here. This is a famous picture. There's the quasar. You probably can't see it. Anyway, really close to a galaxy. So he did these calculations to calculate the probability of a quasar being that close to galaxies. And of course, they said, oh, probabilities don't mean anything. I found this argument to be really funny because, the science, in one science community where they do these things where they calculate the likelihood of some food additive causing cancer, and they get some slight probability increase. They call it a risk increase in the risk of this food additive. And I think we went through this with not saccharin, cyclamate in the 1960s. Cyclamate causes cancer, and it was based on these probabilistic arguments. But when he applied the arguments to quasars being in nearby galaxies, that can't be right. That's just sheer accident. Just sheer accident. We can't accept that. It's all accident. And well, he didn't really like this, so he started looking for quasars near galaxies, and he found a whole bunch of cases. He found a case where there were 3 quasars near a galaxy, and calculated the probability of this happening by accident as being some ridiculously high number, millions and several millions. Well, that doesn't count either. That's not good evidence. It's all just accident. So,
what about the resolution? What do we mean by a quasar near a galaxy?
Well, I can only, I'd show you the picture, but you want to see the picture? I'm not sure the picture is going to be that helpful to you.
Well, I mean, if the resolution is sufficient, how is it determined the resolution for the position of the quasar and the position of the galaxy to be sufficient to determine that they're in fact in different objects?
Do you see this picture? You see the galaxy there, and there are these bright dots around it?
Yeah.
Those are quasars. Well, there are 3 of them that are labeled in this picture, although they're hard to see. There's 3 of them, and they're kind of in the fuzz that surrounds the galaxy.
Okay. Oh, okay.
Presumably, the main people are saying that these are mere line of sight illusions. The quasar is very much further away.
Right.
Not beside, yeah.
Yeah, you can sort of believe that, but what that gets you to the story of they didn't like this, so they took away his telescope time, so he couldn't make any more discoveries and point out any of these instances. So that's a case of what are we going to call that? Censorship? Is that censorship when you take away your telescope? Is that censorship? Suppression of dissent? Is that an example of it? How about maybe it's an example of intolerance? These are
It
all
was expulsion in a way because he left and he went to Germany, didn't he? He left the
right.
USA.
Yeah, it's actually surprising that the Germans gave him a job,
Yeah.
but I don't think, I don't know how he did manage to continue on his work, and I'm not really, I don't really have at my fingertips any real comments on that. Um, so it is kind of surprising that he managed to continue to find you know find these things. I think one of the problems was that his argument was that the quasars were ejected from galaxies. Okay, and so then people said, well, wait a minute, how is this possible? We have to have a physical law that explains how quasars are ejected from galaxies, and we don't know of any, so therefore you can't be right. Which I find kind of interesting because it says theory is supreme and evidence is not to be accepted if it disagrees with our theory.
Putting the cart before the horse.
Right. Well, his argument
Well,
was, well, I don't, I have a theory and, um, it looks like, well, it had been pretty well established that from radio sources that the radio sources were ejected from the centers of galaxies. And that was that was pretty well accepted. And primarily because when you look at the maps of the radio sources, you can see that the sources are these things that are out beyond the galaxy in the center. And as you go closer, the radio sources kind of slim down. And in some of them, you can see a stream coming out of the galaxy that then emerges into these broad areas of radio emission. So the idea was that the radio galaxy ejects the material, these high energy electrons that are spinning around in magnetic fields. And so they're ejected by the galaxy. But when he said, well, I think these quasars are ejected from galaxies, they didn't like that idea, which kind of makes you wonder, like, why you accept one idea but you reject the other. Okay, we don't have any comments on that. All right, we're coming up here with a minute left. So anybody have any comments before we go to the last segment?
well, following up on Ian's comment about line of sight, what evidence is there that, for example, in the picture that you showed with three quasars around a galaxy, that those three quasars are actually close to that particular galaxy, or even to each other, in terms of they could be
Now you're
vastly different distances.
now you're arguing in favor of the intolerant establishment.
Well, I don't know what I'm arguing, but I was just asking a question as to how would one determine that the three quasars shown in that particular picture, just as
Well,
an example.
you have to know what their distance is. You have to measure their distance, but you can't measure their distance because their distance is measured by their redshift. But if you believe that the redshift is a measure of distance, as the establishment people believe, then you immediately assume that the quasars are behind the galaxy, and it's a pure accident that they appear to be close to the galaxy as we see them. But in order to believe that, you have to believe that the redshift is a measure of distance. Correct? No answer. All right. So the problem is if you measure the distribution of quasars on the sky and you know what the probability is of finding any quasar at any position in the sky and you calculate that probability, it turns out that it's improbable that they would be located at a position on the sky, three of them near a galaxy. So the probability of that happening by chance is shown statistically to be very unlikely. But because we're using a statistical argument, you can always say, well, that's just an accident. On the other hand, when scientists want to argue about cancer risks and that sort of thing, they have calculate these very small probabilities of cancer risk and tell us that we need to ban certain substances because our health is endangered by the probabilistic results of their probability calculations. So they want to have it both ways.
Again, it's another example of being influenced by what you want to believe and interpreting data in the best light, and which would contradict as little as possible what you wanted to prove in the first place.
Well, that's really the point, isn't it? So if you believe in religion, your idea is if it's a religion, you must believe because that's an article of faith. It's an article of your faith. There are certain assumptions that you make that you assume to be true as part of your religion. That's my understanding of it. Of course, I could be different. Okay, so I have a phone call. I don't know if you can hear it. I'll let the phone ring. Um, Anybody else have any comments?
Yes, I have.
All right, let me go ahead.
He's gone to his phone call, I think.
Okay, because I would like that he will hear me because I want to give some very solid arguments against religion. Big Bang model, it's religion right now. It's not science. I'm so sorry, guys. My understanding of science, you have some hypothesis, you have some postulate, something like this. You believe in them. And then it must be logic. Logic, solid logic. You cannot contradict yourself to your hypothesis. One of these hypotheses, general relativity, vacuum. Vacuum instead of cosmic medium in my place. But what is important, Friedman, in a few years after this general relativity equation, solve these equations for the perfect fluid. The first my question is, it's vacuum or it's a perfect fluid? Everybody refers to Friedman equations and nobody pay attention that it's a perfect fluid with pressure, with mass density and all this stuff. That's why you cannot build any theory based on the first assumption or postulate, whatever. It's contradict each other. You have your vacuum or you have your liquid, perfect liquid. The second very important point, you believe that there was initial singularity, then inflation and all this stuff. Show me the place where it happened. Show me the place in our universe where it was initial singularity. There is no even any reference to initial singularity where it is. All this stuff, I don't like it. If you put something, please at least have some confirmation of the main hypothesis. You don't need to explain them. You must believe in them. You see the difference between theory and hypothesis. You must take your hypothesis as a belief, as it is in any religion. But then logic, I believe, okay, there was initial singularity. Show me where it is. I don't want to ask you, what does it mean? We infinite energy density, all this stuff, but at least show me this place. The
Well,
next,
I think I've heard Big Bang theorists suggest that the Big Bang happened everywhere. That the initial, like, I know it's outlandish. I mean, I don't agree at all. However, though, within the first few microseconds, Like even in the book, the first 3 minutes by Steven Weinberg or someone, they said the Earth was like, I mean, the universe was the size of an orange. It had definite size. I mean, but when it expands outwards, why is it suddenly, that there is a central location? Basically, I'm in agreement with you, Vladimir.
Thank you so much. Let me continue because I heard you guys for 2 sessions over. Please let me tell you what I think about it. Harry, thank you so much for very good history of this, cosmology during time. You are the best guy. I have found right now very good points about quasars, about all this stuff. But let me continue with the main, maybe confirmation of Big Bang model, microwave background radiation. First of all, prediction 10 degrees and measure 2.7 degrees. It does matter because, okay, they have no calculations. It's only gas. I don't know where they took even 10 degrees Kelvin. But what is important? The guys, they don't know. They forgot classical physical definitions. What does it mean, black body radiation? Body radiation means thermodynamic equilibrium between radiation and some matter. Some matter must be because photons, they cannot interact with each other. They can't change their energy in any way. That's why it must be some matter inside, outside, but it should be interaction with matter and equilibrium between matter and temperature of the microwave background radiation. It's a reflection of the temperature of the matter around. There is a matter, must be matter. They don't have any matter. Unbelievable. Right now, by the way, fast radio bursts, I talk many times of them. There is a matter inside of our universe. But what is important? Where is the matter? No matter. Next question. How to explain this, microwave background? You have your expansion of your universe, we will talk about expansion too. And because of this expansion, the wavelengths for each photon will increase in size, and then you have this cosmic microwave background radiation. It is unbelievable. How come they could propose this one? The guy who proposed this explanation forgot about double slit experiment. If each photon has a wavelength, then when you're measuring your double slit experiments and you're measuring the path of each photon, you must see interference pattern, but it's gone. There is nothing. One more contradiction. You see, the main advantage of Big Bang model, they predicted microwave background radiation, they explained it and so on and so on, but it contradicts the main problem of quantum physics, quantum mechanics, double slit experiment. I don't understand. And they told us what is the mechanism of wavelengths increase, where the energy going from this photon to where, and so on and so on. You see, even not quasars or all these experimental results. No, even the basis of this model, contradictions only, contradictions. It's beliefs in contradictions instead of some logic. If you suppose something, please continue from this place and go further, further, but it should be logic. If you have your contradictions in your main issues, microwave background radiation, expansion. You have your point about this, initial singularity. There is no confirmation at all. How we can start with this theory to develop something based on nothing? Because there is nothing.
Well,
There were,
yeah, they think they have a theory that's science. It looks to me like it's kind of myth making.
it's a myth making. It's a religion. There was a religion. They put some, points into it, and they are trying not to confirm experimental results. All the time, they are trying to confirm their suspicious myths with experimental results. It should be vice versa. Okay, the second very
Okay,
important.
all right. I want to move on to the point I want to make about this. So, what they call the Hubble tension They have a problem in that when they calculate the age of the universe based on the microwave background radiation, according to their theory, they don't get the same result as they get when they measure the Hubble constant by the redshift brightness relation. So they have what's called the Hubble tension. So their theory is refuted by the observations, it would seem to me. I mean, come out and say it. Our theory is refuted by what we know today, but they
Yes,
call
yes,
it the
yes.
Hubble tension.
Let me continue, and you will see. I will talk about this redshift and all this stuff immediately. But I will tell you immediately, if you are measuring your Hubble parameter according to data of microwave background radiation, you have your age of the universe. They named 14.226 billion years. It's exactly what I calculated. You know, I told many times, cosmic age, cosmic medium, everything depends on each other. And if you will measure your Hubble parameter, not tension, about tension I will talk about right now. You will measure according to data of microwave background radiation, immediately you will get this 14.2 billion years age of the universe. It's exactly the point of my model. But let me continue with this, red shift, blue shifted, and all this stuff. It's bullshits, all of them. You know why? Because to be sure that it works according to their model, they must, okay. Harry, you're leaving all the time because I want you to be part of it. Okay, sorry. What they want, they must start from initial singularity. All the galaxies must go away. Then only then you can calculate all this redshifted and all this stuff. It's absolutely wrong because first of all, there are so many blue shifted galaxies. 10 years ago, it was over 8,000 blue shifted. Our Andromeda galaxy right now, blue shifted. How we can explain all this, theory if that's the neighboring galaxy Andromeda against the theory? Let me tell you what's going on with this general relativity, and it was a very bad move from solar system. The main critical point in physics, and physics started with solar system, with planets, with moves, with Newton and all this stuff. And we must continue this classical physics to the galaxies. According to my understanding, my model, we have not solar system, we have galaxy system, superclusters. There is a center of supercluster, and all galaxies moving around this center of superclusters. You see, it's scale factor only. Have your planets around the solar system. Now you have your galaxies moving around the center of supercluster. The same idea, but different scale. Instead of planets, you have your galaxies. What is important, it's confirmed already that we belong to our Laniakea supercluster. There are 100,000 different galaxies moving around this center. They are not moving from initial singularity. They belong to this Laniakea supercluster. And many times I compare it to solar system. Guys, all the time we can to take a look on Mars, on Venus, or something like that. Sometimes they are moving toward us, sometimes out of us. You will measure this blue shift and red shift. You have bullshit. It means nothing. It's moving one against another. Supposedly, they are measuring even redshift for the center of our Laniakea supercluster. It's 0.07, something like this, it does matter. But what is important? It is not center of our supercluster moving against Milky Way galaxy. Vice versa. Center of Milky Way galaxy moving against center of the cluster. You see the difference. It's a different law, totally different story, and these
Actually,
conflicts,
I don't
all
see
this,
how this is.
conflict.
What is the point that you're making related to the theme that Harry presented? It
No,
seems
he
like
talked
you're
about the
just
treatment, yes.
rambling on about a whole number of things. What is the
You
point?
don't understand. You didn't start from the beginning. Okay. The theme of today was religion or science. Do you know the name of our sessions today? The title? Ah, you don't know. I'm so sorry. Please take a
Yes,
look at least what
that
was the
was the
meaning
theme.
of
So,
this session.
what
Okay,
is the point
right.
that you're making on that subject?
He's trying to show that the current thinking is religious thinking of cosmology isn't really consistent with other knowledge that we have regarding classical physics. Um, that's kind of it. And what's kind of happened in recent years is that there's a lot since the book that I was referring to, different approach to cosmology, was published in 2000. That's like 25 years ago, and a lot has changed since then. And it's kind of gotten worse. It hasn't gotten better for the establishment viewpoint. It's kind of gotten worse. We have like the fact that the microwave background calculations don't agree with the Hubble redshift relation calculations. That's called the Hubble tension. And the other point that he's made is that there's been this discovery of all these super clusters, the clustering, which negates the assumption of homogeneity assumption that's used in general relativity. So, and that's kind of interesting. I mean, the idea of what the universe looked like, 25 years ago is not really what they think the universe looks like today. And but they're still holding on to the Big Bang ideology. And they're trying to find ad hocs, although they've ad hoc'd it quite a bit. They brought in the dark matter. So the universe has to have dark matter, and then the observations didn't agree with their theory, so they had to bring in dark energy. So now the universe is like 2 or 3% matter, and the rest of it is dark energy and dark matter. So when are they going to, decide that their theory, the Big Bang idea, is just not working out for them?
Well, it could be that decision is underway as we speak, because I don't know. Perhaps others here have seen what I've seen. For example, on YouTube, there just seems to be almost no end to the videos uh, along the theme that there's a crisis in cosmology. So, in other words, your whole theme, Harry, that there is such a crisis, if I'm okay in interpreting it that way, um, is being promulgated out there in the social media. In
Right,
other
but
words, it looks like the
Yes,
people
Jim, but
holding
you
on
have
to
to
the
go to
Big
the
Bang
social
theory
media to get that
are,
information,
are are almost a minority now. Go
such as
ahead,
YouTube.
Ian.
What?
I
I'm
mean,
sorry,
I think the
Ian. What
point
were
is
you
that in the
saying?
orthodox publications, you will not find this dissension. You'll find it in the social media, but you won't find it in the orthodox publications in general.
Not yet. Okay.
Okay, maybe for the future.
I would also say that this crisis in cosmology has kind of existed from the get-go, if you will. The Hoyle in his book is essentially, that's what he's talking about. He's talking about crisis in cosmology. These but they tried to fix these problems by, like in the case of ARP, they took away his telescope time. In the case of Hoyle, they put forward a false refutation of his theory, and so preserve their preferred ideology by doing that. So they've used various mechanisms to preserve the orthodoxy. And the question is, I guess the question that's been raised by Jim is this orthodoxy, the orthodoxy that exists in the textbooks, is it going to survive the recent cosmology crisis? brought about by the JWST telescope and the fact that it doesn't really appear to be confirming the ideology that they've been teaching students for the last 50, 60, 80 years.
They will have to modify the existing ideas somewhat, perhaps by just fiddling around and introducing ad hoc
They've already done that when as I mentioned before, when they brought it. So the Hoyle book, okay, 2000, he talks about inflation. So it was only towards this book was published at about the time when they brought in dark energy, I think. In other words, they were just coming out with the the observations on dark energy, and in the dark matter. Um, so they fixed they already fixed it. They already added in dark matter and they already added in dark energy. So they've had they've had three major revisions: the inflation revision, the dark energy emission, and anyway,
Then
three.
where is the science? Also, at least all of them religion. Where is the science in Big Bang model?
Well, they're preserving the overall paradigm. The paradigm remains intact. The Big Bang cosmology, it's been modified quite heavily, I think. First with the inflation, then with the dark matter, and then with the dark energy. So, what modification are they going to bring? What's the upcoming modification? The ad hoc thing.
They don't have them at all. They don't have. But even dark matter, it's a principal point. Where it came from? What is the source of this dark matter? Dark energy, nobody knows what at all. What does it mean? They are solving all equations, and that's it. There is no meaning for all these notions, even. If you told me dark matter, tell me where it came from. Dark energy, what does it mean? And what is important? Dark matter in dark energy, over 90% of the substance matter of the universe. And you know nothing about this 90% of the matter. Guys, what kind of theory you have?
But
That's
in
why,
nuclear theory,
I'm
you're also calculating age of the universe. That there, it's
I
also
calculate
in the
based
beginning
on the
model.
based on experimental data, based on microwave background radiation only. Cosmic medium is homogeneous, isotropic. All the physical laws depends on the cosmic medium only. That's why 90% of all the matter, I know about it. I gave you the picture of all of it. I gave you at least source. You can believe in my eternal universe. You don't believe it, but at least I gave you the source of this matter coming continuously to our world. The second very important point, guys, you have practically infinite universe in their model. What does it mean, expansion inside of it? What does it mean? I cannot get it's a part of universe, it's the whole universe expanded. What does it mean? I have no clue. In my model, it's finite, boundless, finite, boundless. Finite can expand, stretch, whatever. But you can imagine it. You have something finite and you can see the growing up, the size of it. But if it's infinite, I don't know what does it mean. Infinite energy density, as a physicist, I don't know what does it mean. All their notions, it's a myth. It's not science at all. As I told you from the beginning,
Presumably,
science, it is postulates, logic. That's it, simple like this.
uh,
There is
presumably,
none.
presumably, what you do is you bring in the students into the universities, and they're bright-eyed and full of wonder and want to learn, and you tell them what the orthodoxy is, and the orthodoxy explains all these questions that you're asking. They have an orthodox explanation for them, and if you don't really accept them, they show you the door. I think that's how it works.
Yes, yes. It's a religion, exactly what was before solar system. The scientists were even burned. because he told, no, center not our Mother Earth. Center is sun, solar system. Can you believe it? It's the same story. Now they are killing any new ideas, any new model, because it's against their myth.
Yeah, well,
Well,
that
I
indeed is a
already
problem
discussed that. Huh?
because
Go
it's
ahead.
self-perpetuating. So in other words, like the church would bring in young people, novitiates, and they would be taught all the orthodox doctrines, and they mustn't question them, and then they become the establishment. So it's
Right.
self-perpetuating. Same with science. We're getting youngsters in. We're not letting them think. We're bringing them into university. We're actually indoctrinating them into conventional science, and then they, in turn, become the professors, um, which are laying down the law for others. So it's a self-perpetuating. So there certainly is an analogy there between science and religion, indeed.
That's actually why I think that any sort of revolution in science should arrive outside of universities. As outlandish as it seems, there should be independent people just to step up and like say, hey, there are all these unanswered questions, that we can present to you. We're a friend of science. We have the same goals, except we differ. But here are questions. I mean, maybe it's in the distant future this may happen. I can't see relativity and the Big Bang being taught 100 years from now and being as orthodox as it is now. I personally don't think it's possible. Maybe it is, though. I don't know.
And maybe the meta question is what motivates uh, determining a beginning time of the universe in the first place. That's straight out of Genesis, let there be light theory.
Um, yes, but then on the other hand, you have the problem of the steady state theory, which is how is this? I don't believe in spontaneous creation. So, what are your alternatives? Creation all at once, or creation, as an ongoing process?
I would say it's possible that all physical phenomena has always existed in one form or another. Uh, I don't see. I can't see a beginning of things. Like, what would be the mechanics of it? Like, how to explain it?
Right, but then what are you going to do when the little boy says, "Where did the sun come from?"
Well, science is complex anyway, and to describe them the Big Bang takes a lot of thought and effort. Why not project that same thought and effort into saying, well, hey, we don't know. These are the accepted theories. These are alternate theories. Just instilling in them a sense of inquisitiveness, I would say.
Jerry, you have only very, very simple question. I will tell you right now. Steady state, universe forever. There is no beginning. You have inflation, initial singularity, all this stuff. All the matter inside of one point. Can you explain, baby? What does it mean? All the matter, all the galaxies, everything in one point, and then inflation with a speed much, much higher than speed of velocity, speed of light, and all this stuff and so on. How come? Or there is another choice. There is a beginning, something small with small energy, matter, and all the time continuously saturating from outside. What does it mean outside? You cannot explain, but at least you have some beginning, you have something solid. You can find the size and energy density, all this stuff, and then to create all this galaxy, you must have source of matter where it came from. You have no
What is
choice.
the scientific payoff for defining a beginning?
It's not
Isn't there enough
scientific. It's a
mysteries
principal
about the
point.
universe as we now know it? For example, uh, Harry in this session today just ran through a whole list of mysterious phenomena. Isn't there enough there to study without having to worry about where it all began? you
I,
know,
I
perhaps
put
we
my
should just
comment,
learn a little
Jay.
bit more about the universe that we have today.
I would
Well,
say
one
I
could
would
be
say if
very
there was a
cynical and
begin,
say that
I,
the scientists have capital in taking over the position of religion. They say, look, religion just gives you
Aha.
some idea, general idea, but we can actually tell you exactly how everything started. So we're the new high priests.
Right.
Well, I would personally say that any theory that suggests a beginning requires that something arose out of nothing, which seems impossible to me. I mean, how did something just suddenly pop into existence out of nothing to begin
Well, you've
everything?
got to throw away all everything that we know about physics. You throw it all away, and then you've got a beginning.
Well,
And
But there's a
mathematics.
lot of scientists that don't want to throw away everything we've learned about physics in order to postulate such a beginning time.
One of my mathematics lectures in college, I used to talk about the 11th commandment, which you must not disobey. That was, thou shalt not divide by zero at all costs in mathematics. But that's exactly what the Big Bang does, the singularity. You're dividing by zero.
It's good. James, there are two options only. All the matter in one point, Big Bang model, or all the matter coming continuously to our world. There is what is your choice? James, in your model, what you have in your model? Stable state, theory, steady state? What is your model? You're asking the question. I
My
want to ask
model,
you a question. In
great.
your theory, what is the beginning? If there is no beginning, what is your model based on? What is the
Well,
principal
but
point of
the
your
binary
model?
mechanics cosmology that I presented right here in these sessions um, explains basically our focuses on creating the universe that we have today and understanding how it operates as best possible. Um, and that's quite an achievement when we think that only a few decades ago, people weren't even aware of galaxies outside our own Milky Way. And now all of a sudden, we're going to pin down the exact age of the universe. I mean, give us a break. You know, like it could be we need decades of study of the universe we have now as and understanding it better. Harry just listed this morning. What is it? A half a dozen or more mysterious phenomena that are not quite that are only barely understood. So you know, why do we have to even think about the age of the universe and things like this? Well,
You
I guess
answer
if
my
you're a
question, please.
creationist,
Please answer my question. Don't name anything else. Your theory is a steady state theory or what?
well, it's well, I'm not sure exactly what you mean by steady state because
You don't
everything in the
understand what does
universe
it
is
mean steady
changing.
state?
Change is the name of the game in the universe today.
Universe.
So, what
Tell
is in
us the name
steady
for
state?
your
Well, I
universe.
have no idea what you're actually meaning by the
okay.
term
All
steady
right. We
state.
need to finish up here a little bit. Um, I want to sort of comment a little bit on. I think the question kind of that I was bringing up was that you have the steady state idea, okay, and then what's the steady state idea based on? Well, it's based on a theoretical idea, this perfect cosmological principle. But what they're really trying to do in developing that idea is they're really trying to stay close to the observations. And so what happens is that the establishment, if we want to call them like a religious group, is adhering to this idea that the universe had evolved from that. So everything existed at the beginning at some point in time, some initial miracle, and evolved over time. And they really are not interested in observational evidence that refutes that particular idea. So that's kind of what makes it a religion or had this religious connotation. The dogmatism that there had to be this creation, there had to be everything in the universe was created at this instant of time, and then the universe evolved from that initial whatever creation event, the miracle at the beginning. And
Vlad's cosmology is in the same category. Is what you're saying is that the evidence is not supporting
exactly he's not exactly saying that. He's saying something different, and you're not really getting the difference in what he's trying to say.
Well, he says that there's a beginning time. That's getting pretty close.
We've argued about this over and over and over again. I don't see the point we're going to solve it in the next 5 minutes. The point
that's my point. Let's understand the universe we have today.
We only have a few minutes here. I want to point out that there is this difference of opinion, and a lot of the difference of opinion results in, is the theory right? And if you believe the theory is right, then we must discard certain evidence, unless that evidence can be integrated by ad hoc assumptions into preserving our paradigm of the Big Bang. So, for instance, they created dark energy, they created dark matter, they created inflation, attempts to integrate evidence that doesn't agree with their theory into the theory by creating these, moving the goalposts, as Roger would say, ad hoc changes to the theory. The complaint that people like Hoyle and Halton Arper saying is, shouldn't our method be to look at what's happening in the universe and coming up with a catalog of things that are happening in the universe and trying to understand what those things are telling us about the laws of physics? Not necessarily, and the answer to that is, we already know the laws of physics, and so you're not telling us anything that we want to hear because your discoveries contradict our laws of physics. We don't want to have any new laws of physics. We already know what all the laws of physics are. So you have these two different approaches to doing science.
By the way, just a question about Hoyle's position. Because if I understand you correctly, you seem to be implying that Hoyle kept with his steady state theory. But the accounts that I've read, they may be incorrect. They sort of say, oh, well, even Fred Hoyle was forced at the end to admit that he was wrong.
Yeah, right. Okay, that's mythology. In this book, he talks about his modified steady state theory, which they call the quasi steady state theory. That's in the later chapters of the book. And I found it difficult. It's pretty dense and difficult to read. I don't think Hoyle ever accepted that his steady state, maybe in the original form of the theory when it was very primitive in 1948 or whatever, maybe he said, oh yeah, okay, that could be modified and we could come up with a new theory. But I don't think he ever really wanted to believe in the Big Bang. I don't think he ever gave up his resistance to that theory.
Well, that's interesting.
But I just read his book. It's a tough read. Maybe there are other things that you can read or other sources. I think that's an example that you just cited, which is, well, if we can show that the main opponent of the Big Bang accepted the Big Bang was true, then that's a mythological argument, I think. That's just pure myth. Okay, we got a minute left. Thank you all for coming here today. And I hope this was entertaining and informative.
Good job, Harry.
Yeah, thanks so much.
Sure.
Y'all have a good day.
Equally.
All right, we got 30 seconds left. So does anybody believe that science is religion now? Okay, so we got
religion. Science. It's not religion. It's science.
I'm going to try to get my quip. The difference between science and religion.